Hi, we are Group 9. In this video, we will present our re-implementation and extension of KinectFusion. In the augmented reality, it is crucial to reconstruct the surrounding surface. This video shows an interesting application on Apple Vision Pro. With the detection and reconstruction of the floor surface to add the coins, it makes cleaning a fun game. In this work, we re-implemented KinectFusion to explore this pioneering method for real-time dense surface mapping and tracking.
Fusion is a real-time mapping pipeline, uses Kinect sensors to create accurate 3D maps. It operates through a series of iterative steps. Initially, the process begins with surface measurement, which is a pre-processing module. Following this, surface reconstruction is used to fuse depth maps into a comprehensive global volume representation. And surface prediction uses raycasting to generate depth map from the fused volume. Finally, pose estimation utilizes ICP to estimate the camera pose. Let's get into the details. For surface measurement, we first apply a bilateral filter to depth maps to reduce the noise, and then we back project depth maps to acquire vertex maps. And for normals, we estimate them using the cross product of the 4 neighboring pixels. We calculate vertex and normal maps on different resolutions. For surface reconstruction, we use the depth map and pose estimated by ICP to integrate new information into the global TSDF volume. To achieve this, we project each voxel within the camera frustum onto the image plane to obtain the observed depth. In this example, voxels on the same row are projected onto the same pixel, resulting in identical observed depth. We then compare these observed depths with the measured depth. A measured depth is calculated using the camera position and voxel location. If the measured depth is less than the observed depth, then the voxel is in front of the surface and vice versa. When both depths are equal, we have identified a surface. Throughout frames, we maintain a running weighted average of the TSDF values in order to always have a single TSDF volume in memory.
After the TSDF volume is updated, the third module is surface prediction. For each image pyramid, rays are shot from camera through each pixel in image plane into the volume. We compare the TSDF value in voxels along the marching ray. When the TSDF value crosses 0 from positive into negative, we pass the surface and find the intersection point. The predicted vertex and normal at this point will be stored into normal map and colored vertex map. In the fourth module, pose estimation, we take the current maps from surface measurement and predicted maps from surface prediction as input. Then we find the correspondences between these two kinds of input by filtering the distance between vertices and angle between normals. Afterwards, we apply point-to-plane ICP to calculate the contribution of each correspondence to the pose increment and the GPU reduction or CPU summation to obtain the final result. Finally, we will calculate the LU decomposition to get the rotation and translation increment and update the camera pose. We reconstructed the tomb dataset both on CPU implementation and CUDA implementation. The reconstruction process can achieve 30 FPS on GPU but only 2 FPS on CPU. We analyzed the computation time between CPU implementation and CUDA implementation. We compared the time to process all frames and per frame. The GPU KinectFusion is 14 times faster than the CPU KinectFusion. We also compare the time each module takes in one frame. All models in CUDA implementation are significantly accelerated than in CPU implementation.
Apart from the reconstruction of the tomb dataset, we experimented with the LiDAR scanner on iPhone 15 Pro. With the help of the app Record 3D and the C++ library provided by the app, we can stream RGB and depth map captured by the iPhone to a laptop and reconstruct our apartment in real time. Let's check the result. I was holding the iPhone and moving in the room to scan the objects. The resolution of the depth map that the iPhone provides is not as high as the Kinect sensor, but we still got an impressive reconstruction result.
For segmentation, our goal was to investigate the feasibility of propagating semantic information from 2D images to 3D volumes. We followed a similar approach to updating surface voxel colors, but employed a slightly modified update rule to mitigate noise present in 2D segmentation maps. This semantic information unlocks many possibilities, including help in finding correspondence for ICP, achieving more consistent segmentation, and mapping and navigating slightly dynamic scenes by categorizing objects into static classes like walls and dynamic classes like humans. This enables us to include only static objects throughout the pipeline. Thank you for listening.